Hello everyone. Did you enjoy taking quantum chemistry for materials scientists this semester? I'd like to talk about Bell's inequality first validation experiment today. In quantum mechanics, an object exists in a state in which several states are superpositioned until observation occurs. So it can only be interpreted probabilistically until observation occurs. An easy example here is the Big Mac and the McSpicy Shanghai burger. After assuming the situation that two people choose only one without knowing each other, when they are far away and check their burgers, state of the burger that exists in the McSpicy Shanghai and Big Mac state will be accurately determined without overlapping. Bohr explains that quantum, which exists in a superposition before observation, determines the state through observation. If we think of it as quantum, let's imagine that there are two interaction quanta. When the distance between these two quanta increases, if we observe that one quantum has a blue characteristic, the other one is immediately determined to have a red characteristic. So I don't know how, but it means that something that can have an immediate effect at this distance is transmitted from one place to another. Einstein described this transmission as spooky at an action distance. And literally, there is a transmission of something like a ghost. According to Einstein's theory of relativity, something faster than light cannot exist. So Einstein could not accept that interpretation because this ghostly transmission interactions faster than light. Tursky and Rosen, two scientists with the same views as Einstein, together create the EPR theory, which refutes Bohr's view. They thought that the locality principle was the basic principle, that such immediately delivered did not take place, and that the state was fixed from the beginning. They thought that there were hidden variables to fix the state of quanta that we don't know about and create the hidden variable theory. The quantum mechanical perspective and the EPR theory were in conflict, and there was an effort to probe what was right. A clue to quantum entanglement began to emerge when John Stuart Bell published his Bell inequality, a mechanical proof of what was right. His basic idea begins with the observations of an observer at position A and an observer at position B. When electrons in an entangled relationship are projected in opposite direction to each other, regardless of EPR or quantum mechanics, as a result, state of A is upspin, the state of B is downspin. This is very clear. And if observer B is rotated 180 degrees, electron B is also observed as upspin, even though electron A is upspin from observer B's point of view. If observer B observes in a state rotated by 19 degrees, electron B will observe upspin or downspin with a probability of 50%. Observations in this twisted state of the axis were the beginning of the idea of Bell's inequality. According to EPR theory, the spin state of entangled quanta is always fixed. Therefore, if the spin of electron B is observed from observer B tilted by 10%, electron B will spin up with a probability of 1 out of 10 times. In quantum mechanical analysis, electrons exist in a superposition state of upspin and downspin. And as soon as the state of an electron A is observed, the state of B is determined immediately. If observer B is tilted at 60 degrees, the spin state of electron B can be determined probabilistically, and the probability can be obtained as follows. You can show in this slide here. So if you do the calculations, there is 75 chance of downspin and a 25 chance of an upspin. This expression is Bell's inequality and is a mathematical expression of the preceding phenomenon. As shown in this graph, blue is the quantum mechanical perspective and red is the EPR theory perspective. Depending on each interpretation, different results are derived, and therefore, when the experiment is conducted, the validity of the theory can be obtained when it is checked whether the shape of the graph matches. The scientist who first put Bell's throw experiment into practical practice is John Clauser. He thought it was difficult to actually measure the spin state of electrons, so he decided to use entangled photons. The entangled photons, like the spin of electrons, have an orthogonal relationship. Therefore, the state of the photon could be measured by measuring light using polarization. Calcium atomic cascade was used to create entangled photons. The device he made is shown as below, and it was possible to measure polarized light from all angles by turning the polarization. And as a result, it was concluded that it is correct to interpret the quantum entanglement phenomena in a quantum mechanical way within the range. This experiment is significant in that it was the first best quality demonstration experiment. Although there were many limitations due to the technology of that time compared to various experiments conducted here. Thank you for listening.